Yeah, so this week's content primarily covers the CNN architectures, right? I'll briefly go over the main architectures and then we'll look at a few questions over that. So the very first architecture which kind of revolutionized this whole um, ML field is this AlexNet architecture. So this came out in 2012 by Jeff Hinton and his students, and so for the first time they made use of like the GPU compute to like build build a quite complex convolutional network and see how it performs on image recognition tasks. So the task on which they evaluate this is that ImageNet ILSVRC challenge, which is an image classification task of 1,000 classes. So these 1,000 classes comprise of things, animals, bird species, a lot of things, and so that is quite a hard task, right? So um, yeah, so on that they got something around 75% or something like that, I think, which was really big deal at, at that time. Um, so here you can kind of see there are two blocks that are running in parallel, right? So this is your input image, which is a 224 cross 224 spatial dimensions and three channels, and then there are two blocks running in parallel, this way and this way. So what do you think these two blocks which are running in parallel are? What are all these? So these are all convolutional layers, right, which we discussed last week. So here they actually do this convolution split across two GPUs. Like I mean, run these two things in parallel. So that is, they divide the total number of filters by two, and then half the filters and they're parallelly processed. So some filters are processed here, some filters are processed here, and you keep doing this, and once in a while they connect between, I mean, they use the feature maps from one parallel block as inputs to the cross between the two feature maps, so that like towards the end the model would have seen all sorts of, I mean, all sorts of filters would have been applied. I mean, all sorts of information would have been extracted, and here finally you get these convolutional maps, um, which is heavily downsampled starting from 224 cross 224, comes down till 13 cross 13 spatially. Then they flatten the spatial dimension, then it becomes like a single layer. Then you can pass it through fully connected networks to like extract dense features, that is the global features of the image. And the last layer is the classification layer, which is the 1,000 class classification here. So yeah, once this showed promise, then a lot of groups which were actively working in computer vision also tried out a different architecture. So a series of like say 2012 to 2019, there were a lot of architectures that were proposed to the other in a sort of progressive logical manner. So in 2014, there's this model called VGGNet, which was proposed by Visual Geometry Group from Oxford. So here so unlike so in AlexNet, so they start with 11 cross 11 layers followed by 5 cross 5 convolution, and then they do 3 cross 3 convolutions. In VGG network, they just say we need not design like specialized filters for each I mean care about the spatial dimensions, because a combination of 3 cross 3 filters can eventually result in a 5 cross 5 I mean a higher receptive field. So suppose did my iPad work? So can I so suppose I want to replace 5 cross 5 filter with a 3 cross 3 filter. Can that be done? Say or a sequence of 3 cross 3 filters. Is this not?
They can be replaced by a sequence of filters.
Sequence of 3 cross 3. Why is that so? So by how many 3 cross 3 filters can I replace a 5 cross 5 filter with? So two 3 cross 3 filters are actually equivalent to equivalent to having one 5 cross 5 filter. So if I need a 7 cross 7 filter, how many filters do I need, like of 3 cross 3 filters?
Three.
3. And what is the computation the number of parameters I have in each cases? So if I have 7 cross 7 filter, I have 49 parameters, right, spatially, into whatever number of channels, into number of filters. So in this case, how many would I have if I replace them? So 3 cross 3 would be 9 parameters, and I have two such parameters, right, two such filters. So I have in total 18 into the number of features, number of filters, right? So it actually the number of parameters and compute required would be lesser but you would be having the same receptive field, right? That you are looking at the same uh, spatial region in the image by replacing 1 7 cross 7 with 2 3 cross 3 filters. Similarly, if I have 3 cross 3 filters, what is the number of parameters I would have?
27 into
27 into f. But if I have a 11 cross 11 filter, that would have how many parameters? It would have 121, right? So it has much fewer parameters, but then we still have the same receptive field. And it's a simple architecture which they scale based on the compute available. You can just scale them. So it's a sequence of convolution and max pool layers where all the convolution layers they just use 3 cross 3 filters. And it's kind of a standard practice which people use not just in VGG, in further later architectures as well, that like you whenever they're reducing the spatial dimension, that is by pooling them, they increase the channel dimension by twice. So by this, say I have an input volume of say 100 cross 100 into 64 after this convolutional layer, and I do max pool. So what will be the volume after I do max pool and passing through convolution 128? Is the like input volume and output volume the same? Because I'm reducing the spatial dimension by 2 and increasing the depth by 2. So does that mean the volume remains same before and after the max pool? It won't, right? So suppose I have 100 cross 100 cross 64 channels. Then after max pool and passing through the next convolutional layer, so after max pool, what would the 100 cross 100 become?
50 cross 50.
50 cross 50, right? So the 100 would become 50 cross 50 after max pool. And then if I pass it through conv 3 cross 3 with 128 filters, what would I get? It would be 50 cross 50 spatially, and then I have 128 channels, right? 128 filters, so I'll have 128 channels. So this would have been 64 earlier. So the volume has actually reduced by 2, right, from here to here, because 100 cross 100 becomes 50 cross 50. So it's reduced by 4, the spatial volume, but the channel volume is doubled. So with time you have the feature dimension volume keeps reducing by doing this pooling and doubling the depth. So after this, so this network called InceptionNet or GoogleNet was introduced, where they question why should we make the filters like fixed as 3 cross 3. We can let the network in parallelly learn all sorts of filters like 1 cross 1, 3 cross 3, 5 cross 5, and so on. So they design these parallel blocks where they do 1 cross 1 convolution, 3 cross 3, 5 cross 5, and so on, all of them, and they combine all the features and get the output features. So the model can look and combine regions at different receptive field levels and combine them. In Yeah, and in this network, they also remove the fully connected layer and make it convolutional. So, how can a fully connected layer be replaced by convolutional network? We had discussed this last week also, I think. Can a fully connected layer be replaced by a convolution of a specific sized by using a specific sized filter?
Maybe using one cross one convolution.
Right, you can use one cross one filters to do fully connected network. So towards the end, when you have your final feature map, rather than flattening and doing full FC layer, it can be implemented using one cross one filters as well. And along with that, they also employ this other strategy where instead of just having the classification network towards the end, so at intermediate stages they basically increase the depth of the network, and at different levels they also add these auxiliary classification networks and train the model. So suppose I, in general, what would I do? I use the cross entropy loss as the classification loss and train this, right? So along with this, even at this stage they say, if suppose these were my features, would that suffice to actually classify them? So at different levels they introduce these auxiliary networks to train classification layers. So after this, like there, then people did analyze how what is the effect of the depth of the network on the final results. So what do you think would happen if I keep increasing the depth of the network? That means I'm making it more and more complex. Does that mean that the accuracy would always be improving, or would it start decreasing, saturate? What do you think would happen?
Not necessary to increase.
Hmm? Come again? It would.
It don't be the necessary to increase
It's
every time.
it's not necessary to increase, right? So when do you think it would stop, or for what might be the reason that it would not increase? So it's a very complicated data set, right? Where I have like thousands of classes and yeah, 1,000 classes and want to classify them.
It might go to the extreme condition like very slow or very fast.
Very slow meaning?
Vanishing gradient problem.
Yeah, right. So why would that? What is vanishing gradient problem?
The loss of when the network's depth increases,
Hmm.
there won't be any effect to the initial layers. Error will be uh, back propagation effects.
Yeah. So there are. So when we are back propagating the error um, through the network, so we usually have these non-linearities, right? Like sigmoid or ReLU and so on. So um, these gradients of ReLU, of a sigmoid function, are bounded. It is not always like huge, right? It is bounded in the region, like range of 0 to 0.25. but then when I am back propagating through a very deep network, so these errors keep getting multiplied, right, due to the chain rule of back propagation. So the early layers would barely have any gradients incoming to them, and they don't the network doesn't learn well. So this is called as vanishing gradient problem. So what would exploding gradients be in that sense? There is another problem also called exploding gradients. So even this happens because of the chain rule, but then there could be some layers where the gradient is very huge at some point. So if the gradient is very huge for some reason at a particular layer, then it keeps getting multiplied, like say at a particular layer at some point 1.5, and another layer it back propagates, it's 1 point something and so on, so it keeps accumulating and the gradient basically explodes. So either cases are not good, which does not really encourage learning. So after some point the accuracy of the model saturate with depth. So is there a fix for but like natural intuition is that if the data set is complex enough, then adding more parameters should actually be helpful in general. But we have these problems of exploding and vanishing gradients. So how can we increase the depth of the network by getting rid of these vanishing or exploding gradients? So to mitigate that vanishing gradient problem, then people came up with these ResNets. So ever since ResNets were introduced, since then to almost till 2020, this idea of residual connection has been a very standard practice, which has proven to be very good, even when you're scaling the network size. So what they do is they introduce something called skip connections like this, where the input we usually pass it through the convolutional networks, and we also skip them and pass it here where we add the input. So suppose like this is some function, right? F, we would be getting f of x plus the input as well. So by doing this, what happens is, so while back propagation earlier, so the gradients would be back passing through only these convolutional layers, right? So convolutional or sigmoid, ReLU, all these layers which can be introducing this vanishing or exploding gradient problem. But now there's another channel for the gradients to flow. So because it is just addition, right? Adding the input, so the entire gradient would be passed here, right? Whatever is the gradient incoming here, the whole thing would be passed back to the previous input. So in this sense, from the last layer, uh, I so these are the residuals which I'm learning, as in it kind of learns. So I'm passing my input. How can I modify my input so that I'm learning something new? So that is what these convolutional layers would be doing, and the gradients would get passed through the whole network, right? I'm creating a channel for it to pass through. So because of this reason, even though you increase the depth of the network, the model is still able to learn, and they showed that so there is ResNet 50 and so on, right, where it's like 50, 100, 150 and so on, where they scaled the network so huge, but still it was able to backpropagate and outperform most of the previous methods. So this was introduced in 2015, and it outperformed like all previous or the best next model by a significant percentage of say 10-15% in a wide variety of tasks. So since then people still introduce modified changed architectures and all, but this idea of residual connection was retained in all the architectures further on. Yeah, so now people did achieve very good accuracy with very deep networks, but then with at the end, if I still need to deploy it, like suppose I want to run a model on my phone, I won't be able to run it, right? Because it's a very complex model which probably requires a GPU which can do so much parallel processing to get my final output. So that is not feasible to do in on these edge devices, right? So to with the objective of scaling it for edge devices, this architecture called mobile net was introduced. So here, they replace the standard convolutional filters with depth-wise convolutional filters. So what are these depth-wise convolutional filters? So here they operate instead of having, say, so dk cross dk is my filter size. Suppose there are 3 cross 3 filters and I have m such filters. No, I mean m is the channel dimension, so it is 3 cross 3 cross m is one feature, one filter, and I have n such filters. So what they do is instead of operating on all the channels at once, they propose to like look at each channel separately. So they call these as depth-wise filters, depth-wise convolutional filters, where I have just a 3 cross 3 filter and I just operate it on one channel. So I'm decomposing this filter into m separate ones. So I have m separate filters, each of size 3 cross 3. I get this. So once I get this, then I apply 1 cross 1. So I apply this and I stack them, right? So I would have got yeah, so after doing this, my feature dimension would be dk cross m, because I've done it on 5 such filters. Now I want to combine the information across channels. So to combine the information across channels, we use n number of filters, where each of them is a 1 cross 1 filter. So if I were using a standard, suppose I was using the standard convolutional filters, what is the number of parameters that for which I can see here? So I have, say, let's just say the filter size is 3 cross 3 filters, and I have 64 channels. 64 channels, and then I have 128 such filters. So what would be the number of parameters in the standard convolutional filters, which is the first, the normal convolutional layer? And suppose I am operating on an input size of 100 cross 100 feature map. and these are my filter dimensions. So what is the number of parameters and the computational cost, that is the number of multiplications I'm doing. So can someone tell me what is the number of parameters in standard convolution?
Nine into 64 into 100.
9 because of 3 cross 3 into
Yeah.
64
64
into
to
120,
120.
128, right? And what is the computation cost? If I have to operate over 100 cross 100, so even that will be of that order, right? Because at each pixel I'll move it over each of them and get this, right? So for now I'm not thinking about padding blah blah etc, but like you get it, right? This is the scale of it. Now let us see what is the filter size when we have depth-wise depth separable convolution. So what are the number of parameters here? We have divided this filters into two stages, right? First is the depth-wise convolutional filters. For this, what would the filter number of parameters be? It would be 3 cross 3 into how many? Into 64. So this is the first depth-wise convolutional filters, and then I have the 1 cross 1 filters, right? So what are the number of parameters of these 1 cross 1 filters? So my M is 64, right? Each filter is of dimension 64, right? There are 64 weights in each in one such filter. And totally how many filters do I have? 128, right? So isn't has the number of parameters changed from the previous network to now? And what is the order of the change? Oh, is this number right? So what are the total number of parameters here? Seven three seven two eight, and here it is 8768. So the number of parameters has significantly reduced, right? Although I'm trying to do like look at the same region in my image and so on. And what is the compute cost for doing this? So for the first filter, what is the cost? The depth-wise convolutional filters, this one, the channel-wise filter. So I have 3 cross 3 filter into the what the each filter's depth is 1 here, right? Each filter's depth is 1, and I'm operating over 100 cross 100 region, right? So after this, so what is the computation cost of performing this 1 cross 1 convolution? It is 1 cross 1, right? The for the spatial multiplication, and then we have um, the depth of the filter is m, so that is 64 into the output number of filters is n, so 128 filters into we iterate over, like we move it over all the pixels in that, right? So 100 cross 100.
Now it should be 98.
Oh, the spatial one you're saying instead of 100. Yeah. That I just for simplicity I ignored the uh, assume you have done padding and doing it. Like if you want to get back the same feature map, you would have done padding, right? And iterate over all 100 cross 100. So what is this value? Okay, some huge value. It's not predicting this. So anyway, yeah, the computational cost and the number of parameters both are significantly reduced by redesigning the standard convolutional filters as depth-wise separable convolutional filters. So this mobile net was like a big step in making it more efficient, and I think around 17 to 19, most like for practical use in industry, almost all networks they used to use backbone of like this kind of architecture to train and deploy, because it was yeah, computationally cheaper. Yeah, then there was this other network called Squeeze SCNet, which is like squeeze and excitation network. So they designed this one like small modification in how convolution is done. so that the dependency between like different channels in the network is accounted for. So firstly they just do like normal convolutional network, so you get this feature map. Over this, in order to like treat each channel in the feature map differently, so they first do a global average pooling of this feature maps. That is, if we have h cross w, right, so you average them, and each channel you get one element then. So this vector would be average pooled numbers, that is you have 1 cross 1 into c channels, right, so you have c numbers here. So then you pass it through a network, a linear simple linear layer, to get back c outputs. So these, they treat them as weights for each of them. So I would have got some numbers here, each of them, and I weigh each channel using this weight, and that forms this I mean, that is the refined convolution block. So this can be introduced anywhere in the network. Like you have these ResNet modules and all, right, here. So anywhere I need, I can add this one squeeze and excitation block to do this, to kind of induce a dependency or a more adaptable way of combining features across channels. So in like mobile net and this, yeah, in mobile net primarily, um, so these are usually designed as flexible networks, as in how much of like the number of filters, the depth, with depth, right, you can change how many so instead of having 64, 128, 128 becoming 256 and so on, I can have a scaling factor for them, where I just scale the network to have lesser depth. So instead of 64, I do say 32, 64, 128 and so on, where I'm so the net so there's a standard network which also takes in these scaling parameters, based on which you can adapt the network so that you can fit it for the compute you require. It's like suppose I have this much memory on my device, so you design a mobile net with keeping that in mind, so kind of like that. So that's why these are like flexible networks which you can uh, tune based on the need, unlike all the previous networks where the depth, like the whole architecture is usually fixed. So yeah, this was kind of a summary of the most networks that there. Any questions or doubts on any of these?
Hello.
Yes.
Can you explain the purpose of SCNet? It's not clear.
uh yeah, I mean, so it is an explicit way of weighing the different filters in the feature map. So suppose, imagine each, each filter would learn some representation, right? Say filter 1 is learning like just filter, like each channel, whatever you are doing here, would be representing say one particular attribute. Say one would be representing lines, one would be representing circles or some sort of curves, and one might be detecting a color and so on. So suppose each channel is capturing some information. So this is an sort of an explicit way of um inducing a way, like weighting across them, to pick which feature is good for me. like if I have to detect say blobs, say detecting arcs could be more useful, right, rather than having lines or edges. So if I have channels which with features which are not really required, it can weigh them less. So it sorts of creates a weighing mechanism to learn more mm, yeah, better representations. It's just a design yeah, simple design change.
Okay.
And this one also is something like, so they use this, they get the global average pooling of this, and based on which they get these weighing vectors, right? So it's something like I'm looking at the global feature map. So usually what happens from when you're going from the early layers to the deeper layers, in the early layers you're only looking at smaller regions of the image, right? And with the depth of the network you would be looking at a more global picture. So here, say it, because of the global average polling done, so it kind of gets a sense of what might be the, I mean, I don't know, like get an overall picture of the image, and based on that create a weighting mechanism type. So you are inducing a global view, I mean perspective, somewhere in the start as well by putting this SE blocks to do this part.
So is it better to put the SC block in front? In the initial layers, I think
Yeah,
we
it
we
makes
will
more
have
sense
to
to put
put the
it
SC
in the
in
initial
the initial
layers.
layers.
Yes.
Okay.
Because in the final
For
layers
better
you would
feature
all.
extraction, right?
Huh?
For better feature extraction, right?
Yes, yeah.
Okay, fine.
So similar to how we design the filters, so these are like inductive biases in the network which you are inducing, right? So that you combine global and local information at intermediate layers and then get your overall feature representation type. Like even designing 3x3 filters and um, in that sequence is to create that kind of inductive bias, right, while looking at the image. So yeah, this is one change in the inductive bias of the architecture. But yeah, it makes more sense that it's put in the early layers, although it could be used anywhere. So if you put it at layers, maybe, I mean, it might not really make much of a difference, or you might just get equal weights and so on. Anyway, for like, I mean, most of these are at least, so these early how these progress, like AlexNet to VGG, GoogleNet, ResNet, till ResNet I think they were very clear. So later it kind of becomes like very custom changes they would have done for some particular cases or to improve efficiency and so on. But the standard practice most people like use is to use the ResNet architecture to make sure that the gradient flows back, and yeah, in general that works fine. And most recently, so these were all convolutional architectures. Most recently there's this new thing called vision transformers. Have any of you heard of that name, vision transformers? Later on in some lecture, yeah, sir teaches that vision transformers. So here we are doing convolution, as in we are like looking at local regions, and then at the end we get the global picture, right? So vision transformers is something different. So there, even from the start, so the image is kind of decomposed into patches, and you combine the information of all the patches, and you keep doing that at every stage, instead of going from global to local. So throughout the architecture you have a global picture of the image. So that is the most commonly used architecture now. It came out in 2020, and ever since then, most CNNs are now kind of replaced by this vision transformer based architectures. So this is the vision transformer is kind of like inspired from natural language processing models, so where they process words, right? So in whenever they're processing language, you process words one after the other, right? So here they make so they decompose, like, so I have a 100 cross 100 image, say I make them into patches, say 9 patches, like divide the whole image into 9 patches, 3 horizontally, 3 vertically. So I get a sequence of 9 patches, and then I treat each of this patch as a visual word. So I have 9 patches, and then I operate over all 9 patches and get a feature, get 9 other features, and then keep doing that. So I keep getting 9 features towards till the end, but still each patch is looking at the all the other patches as well. So there it has global information even from the start. Yeah, that I think it will be discussed in detail later on in the course. So yeah, simple question. So suppose we have an input image of this size 3 cross 64 cross 64, and a filter size, so 3 into, so here when I'm say 3 cross 5 cross 5, what are the number of channels and what is the spatial dimension of the filter?
Three is the depth and 5 cross 5 is the spatial.
3 is the depth, right? That is because I have 3 channels in my input image, and 5 cross 5 is the spatial dimension. So I have 3 such filters, and if I'm moving it with a stride of 2, so what would be the spatial dimension of, I mean, of this output if I use stride 2 and 5 cross 5 filter? I'm not padding it. 64 cross 64 would reduce to what? So what would be the number of the channel dimension of the output? If I have 3 filters, what would be the channel dimension? 3, right?
3.
3. If I change this to 10, what would the channel dimension be? It will be 10, right? So channel dimension is always the number of filters, and then spatially you compute based on their stride and zero padding. So this is the formula, right? So I have, so in 64 cross 62, if I have 5 cross 5, so initially I'll start at what, the first pixel, then the I'll skip the second one, I go to third, skip the fourth one, like this, right? So till where can I do this? Till I go to 60th position I can do, right? If I go to 60th pixel, so 60, 61, 62, 63, 64, so till then I can run it, right? So from like 0 to 60, I'm moving at a stride of 2, so I would get 30 cross 30 dimension, right? Intuitively that is there, but you can put in the values and check. So if I go with stride 1, what would be the output dimension? With stride 1, 5 cross 5 filter, I am not doing zero padding. What would be the spatial dimension? Like, don't even think of the formula. Just see till what pixel
And
can you
5.
move. Huh?
5.
5.
Can you repeat the question?
So here, instead of stride 2, if I do stride 1, that is every pixel I am moving and operating. So what would my feature dimension be, output feature dimension? So 64 cross 64 operated with 5 cross 5 filter with stride 1, that is every pixel I am operating. So what will be my output feature specially?
60 cross 60 cross 60?
60 cross 60, yeah, 60 cross 60 cross 3, whatever number of filters.
Yes.
Because I can go till 60th index, right? I start from 1, first, second, third, fourth, and so on. For each index, I get one output. At 60th index, I can operate the filter because I need 5 pixels to operate 60, 61, 62, 63, 64. So, but after that, because I'm not doing any padding, I can't operate the filter, right? From 61 and so on. So, that dimension will be 60 cross 60. You can use the formula and do, but intuitively also you should be able to figure out how to do that. So which of these two statements are true for ResNet architecture?
A is correct. B is correct.
Yes.
C wrong.
C is wrong. Yes, the whole point was to make it means exploit the depth, right? Yeah, so C is wrong. And what about D?
Yes, maybe.
Uh,
No, using skip connection requires extra parameters to optimize. No, I'm not sure.
no, right? Because what happens here? I'm just adding this. There is no parameter involved here, right? It's just f of x plus x. So in generally, but uh, if needed, like there are some networks where they also employ something here. Um, so in that cases, yes, but in general, no. Skip connection generally doesn't introduce any parameter. So sometimes if you want to introduce a skip connection where say here there was a max pooling layer or some stride to convolution, the feature dimension, the spatial dimension would reduce here, right? If I have a stride to convolution or max pooling, say I start from 28 cross 28 and here the output would have become 14 cross 14. In such a case, I can't directly add it, right? So in such cases, if you want to introduce a skip connection, so they put another conv layer or something here that reduces the spatial dimension also equivalently. Like I can put a 3 cross 3 conv with stride 2 so that it brings it down to 14 cross 14, which is compatible with what is coming out here. But if you are passing it to a position where the feature dimension remains the same, you can directly add it. So there are some networks where they do that, adding skip connections with even in anytime when you have parallel connections, you have to make sure that the feature dimensions are same, right? So for that case, to make them they're equal, you can design your con layers and put them in even in your skip connections. So suppose, when I'm doing that here, instead of 28 cross 14 cross 14, and I'm introducing a layer here, the whole point of putting skip connection was that gradients will pass through here, right? But if I put off another layer here, uh, then even that might reduce the vanishing gradient problem, right? It might introduce. I'm not sure, but while doing this, mm, like if you introduce this, the weights, suppose I want to preserve what is already there and putting this, so like the weight initialization can be designed such that you preserve what you want. Suppose I want to just keep this, then you can initialize the weights to be 0, and this learns a residual. So I want to pass this as is. If I introduce a layer here, you can make all the weights to be like 1 or something, so that it still passes through an identity mapping, but make it flexible. So there are some applications where such things are done. Just don't. But yeah, so in general, yeah, it doesn't require extra parameters to optimize over. So why are one cross one convolution layers used?
I think B, C, and D.
B, C, and D. Yeah. So why do you think it will enable? So what did you understand by this word sequential computations? Okay, by so sequential computation usually is like, so I have to pass my model through this layer, then only I can pass it through the next layer, right? So in InceptionNet, they actually make it parallel, do parallel computations. So introducing that doesn't make my process faster, in the sense that I still need to do what I have to do, right? Um,
D is correct. Only B.
no, D is not.
And to have fewer parameters. To have fewer parameters. Right.
Yeah, to have fewer parameters and reduce the computational cost. We
Okay.
saw even in
Yes, yes.
depth-wise
DMC.
separable convolution, right? Introducing 1 cross 1 layers actually reduces computation.
Can you show the explanation?
So it can't accelerate sequential computation, in the sense that uh, I still need to pass it through this block before I go to the next block, right? It's a VX statement. Let's keep it. Okay, I didn't prepare this, but I think what they're trying to say is, uh, see, suppose I'm replacing the whole field, like I'm doing in depth-wise separable thing, then I'm actually reducing computation. But here, although I so these computations need to have, I mean, they do happen in parallel, but still, it I can like go to the next step in the network only after doing this, right? One after the other sequentially. It's not like I'm skipping something and moving over through 1x1 filters. That's what they're trying to say, I think. I'm not sure. Anyway. So, how many of you are aware of efficient nets? I didn't discuss it today, but it was still taught in the lecture. Yeah, so based on your understanding, which of this is right?
The first one is right.
Yeah. So it is similar to somewhat similar to the mobile net one, where they can scale the depth, right, in the similar sense. So here they design the network such that they have three scaling factors: one for depth, one for width, and one for resolution. So if I scale all of them, suppose like I want to double my model size, reduce it by half or something, so I can decide on a scaling factor based on a formula that depends on depth, width, and resolution. So the architecture is based on this. So yeah, I mean, although it was introduced in efficient net, it can, the principle of scaling is the same, right? You can, in any architectures, I can choose the depth, width, and the resolution that will fit my compute budget. So even B is true. So I see, right? C and D.
C is right.
C is right, right? I mean, the whole point of efficient net is that given a budget, how do I choose this depth, width, and resolution so that I can like make use of it fully, but still perform well type. Design a nice architecture to fit that in. They take long time to try, and not necessarily. It's not dependent on that, right? So the last one is false. So why did now suppose mm, so what are the so do you guys know a difference between parameters and hyperparameters in these deep networks? So what are parameters? What are hyperparameters? Have you heard these words?
The parameters are the weights that the model learns,
Hmm.
where the hyperparameters are things like learning rate, which we manually set.
Yes, so any parameter which we manually set are usually hyperparameters. Yeah, it could be learning rate, choosing an optimizer, even these things, right? Depth, width, resolution, filter size, all of these are hyperparameters. So whenever we are designing a network, mm, so it's very hard to decide these things, right? Like how many filters should I use, the number of, the number of filters, spatial dimensions, should I put a residual connection or not. So all these are quite complex decisions to make, right? Even a lot of this has come out through experimentation, and people just keep some ideas which has worked and then they keep trying something new. So in that sense, so suppose you have to um, so you're given with a completely fresh data, and you have to completely fresh data, and you have to design a network that works well, and you want to run it on a simple small mobile device. So in such a case, if you had to pick one network, which one would you pick in all the networks which we have seen until now?
Efficient net.
Efficient net. Why so?
Uh, yeah, budget constraints, one thing. Then
Yeah, all the reasons
we
which
can
are, which
achieve
are here,
maximum
right?
accuracy. Yeah, all the reasons, yes.
All these are applicable.
We can achieve maximum accuracy within the budget and
Yeah,
yes.
and more so because, so suppose I know a particular model like ResNet does well in a classification task. Say I have like ignore the compute part. I have a ResNet, a VGGNet, AlexNet, all of them which are equally complex, as in which have same number of parameters, about the same number of parameters, and I know that ResNet works well for that task, for a particular classification task. Now I have another very similar task, and I have to pick one network, but my compute budget is very low compared to that. Say I can't run a ResNet 150. So what you can do is, so you can hope that whatever the depth, width, and resolution which is used in ResNet, if I scale it down by that a particular ratio following that efficient net rule, and if I scale them down, you hope that those properties of the ResNet would still carry forward, and you use it within the budget. Okay, then that was pretty much what I had planned to discuss. Yeah, any questions? Or I'll go over the code notebook for today's part. So, yeah, yeah. Let's do this. So now you guys have seen these architectures, and then have seen how to train a model and all that, right? Now, like, can you guys name what are the ingredients of training an ML model? Everything, the whole pipeline. Suppose I give you, say, like a bird's data set, where the task is to put them into which categorize them into the different species they belong to. So you have this data set, Now you have to train a model. Um, Obviously, it's a vision data set. So, what all are the things you should take care of? So, from the start to now, if you can think and name what all is required, the different, what all are required, what kind of decisions do you have to make, design choices, and what algorithms would you use, how would you train, how would you test. So, like, maybe take a couple of minutes and name these different aspects of training an ML model. Forget what is the choice. I mean, picking which model we'll worry about later. But you have to pick a model. So just name me things. So what are the steps required?
So
And
first we
which
have to
data set you are using.
Data set. Fine. Data set I've given bird species. So with the data set, now let's just deal with the data set. So using this data set, what all I might have to do? If I have to prepare it to use it actually.
like first split it into test train and validation,
Yeah, train,
then
test.
shuffle it properly.
Well, and
Shuffle it properly.
shuffle. Yes. Shuffle it. Yes. Anything more which I'll have to do on the data?
And feature extraction, which are meant to differentiate.
So let's just do a CNN. No, forget feature extraction. Let them learn on its own. So
Okay.
assume a deep network, right? So I'm not
Okay.
doing any hand. I don't want to do handcrafted features for a deep network. What do I have to do?
Maybe some kind of augmentation we can apply.
Augmentations. Yeah, you can apply augmentations. Yeah, some pre-processing basically. Augmentation is a not a necessary step, but are there any necessary steps which are usually done? So this is optional. This is like just so that you create variations, right? One normal thing is doing normalization. Normalization, right?
channelization,
Mean
training.
variance normalization for better learning. And yeah, depending on what kind of like take care of what your channels are, in which order you should know them, so that because while testing time you'll have to create it in the same form, right? Different libraries, all that, what kind of how it will read the image. You should be careful and aware about the be aware about how the data is read. These are very simple things, but then they can create issues. Suppose while I'm in my training pipeline, I've used the pillow library to load the images and so on. Then while testing, I say I just load it using OpenCV and then test. I might not be getting correct results. It might be because of a simple fact that while training, I might have used BGR channels, and this might be testing on RGB. So the features, everything will get messed up, right? And it might not classify. So a bird won't look the same if I see it in RGB space versus BGR space, right? It's just simple things, but something you should be careful about. If you actually implement, then you would know like these kind of issues will face if you are not taken care of things. Yeah, so fine. Now I've created train, test, validation, split, shuffled them, pre-processed my images. Now what else? Anything else to do with data? Or if I have to use this data while loading, what else could I specify? Any hyperparameter?
Batch size and things like that.
Yes, batch size. How much you can use? Yeah, batch size. It could be 32, 64, 128, whatever, depending on how much my GPU can support. Okay. Anything else with dataset?
Epoch.
Epochs. Yeah, will come to the training part. Anyway. Okay, fine. Now we've prepared the data set. Now, what is the other important thing which I should pick?
Setting up the hyperparameters.
Hyperparameters. Okay. Yeah, the epochs and all will come under this. So name the hyperparameters. Number of epochs, as she said. Or what is an epoch, by the way?
And the number of iteration.
Number of iterations.
The number of iterations through the whole data set.
Whole data set, right? Yeah, one iteration throughout the whole data set. It's called one epoch. It could comprise of, depending on the batch size, one epoch could have any number of iterations, right? So suppose I have my data set size is 1000 images, and with batch size 32. So how many iterations would is equal to how many iterations? If I have 1000 images running with batch size 32. So iteration is one pass, right? One pass over the model. That is like one batch of data I pass, and I do forward pass, backward pass. That is called as one pass, one iteration. So how many iterations will I do in one epoch?
30 plus iterations.
30 plus iterations, right? Some
Batch
33
size is
odd.
32.
33 or 34, right? 30, it'll basically be 1000 by 33, that's all. So these many iterations I would need one epoch. Okay, after epochs,
Loss function optimizer.
loss function optimizer. So
Learning rate.
learning rate. Okay, what all loss functions do you know?
And cross entropy.
Cross entropy loss. Anything else you're aware of? Anything you heard
Mean
of?
square error.
Mean square error, yeah.
Sigmoid.
Sigmoid loss is CA loss only. Binary CA loss, essentially. Yeah, there are some other things like margin loss and so on. Margin loss, if you've learned about SVM, could use SVM loss and so on. Anyway, yeah. So these are all losses which you can use for classification. MSE is usually used for regression. And optimizer, what are the choices of optimizers? What all optimizers have you learned about? Name them.
Adam optimizer.
Adam. What is the most common basic one? You're telling all the advanced
Adam?
one. No, Adam is the last one you learn, if I'm not wrong.
Stochastic gradient.
Stochastic gradient descent. SGD is the most basic optimization function, no? Adam, AdaBoost. So before this, what comes?
Gradient descent.
This is gradient descent.
Batch gradient descent.
Yeah, all are gradient descent versions. Batch, mini batch. Yeah, so what are the difference between batch gradient descent, mini batch gradient descent? Anyone?
In batch gradient descent, the parameters are updated after every mini batch. While in the normal gradient descent, it is updated after the epoch. So,
Yeah, in mini batch it is updated over every batch. In batch gradient descent or like normal gradient descent means it sees all the data and then updates the loss, which is practically not done at all. So practically what we do is mini batch gradient descent. So SGD, there are this momentum optimizer, all that, right? Momentum, RMS,
Adagrad.
Yeah. AdaBoost. What? Fine. Learning rate. Okay. Yeah, learning rate will keep something. It's usually kept as some 0.1 some to 0.01 or something in this range, in this order. Then one other thing which you could do is pick a regularizer. It's not a necessary thing, but an optional thing. Regularizer. You could do like dropout or have L2 norm, some such things, right? L2 regularization. There are many different types, no? Lasso, something, and all those things. Some regularizer. Fine. Yeah, like I think these are sufficient number of hyperparameters, basically required ones. Now what? Fine, you have hyperparameters data set. You have to pick a model also, right? Now name all the choices of models which you have. If for a CNN, if I have a CNN,
I'm AlexNet.
CNN, deep CNN, RNN.
what is
Is that
RNN?
used for recurrent neural network?
I'm regional.
Yes,
No,
recurrent
no,
neural network, right?
no, no. RNN is recurrent neural network. But have we discussed recurrent neural networks yet?
Actually, we have discussed RCNN.
RCNN. But
It's
for
in
what
the
problem?
6th week, I think.
That comes in future. No, let's not think about it now. For now. But okay, you mentioned the name RCNN. Why is RCNN used? For what problem?
Object detection.
Object detection, right? Currently my task is
Yes,
classification.
ma'am.
So for classification, what the architectures we discussed today, right? Any of those can be used.
AlexNet, InceptionNet.
AlexNet, VGGNet, Inception, MobileNet, any of them. ResNet. So you can pick an architecture. So each of this architecture is usually defined by a fundamental block, right? Like VGGNet has those conv layers followed by pooling layers, and you keep repeating them. Scale. So the number of blocks defines which VGG it is, which is VGG16, there's VGG19, like that, right? Even in Inception, there's that fundamental block, right? Which there's parallel 1 cross 1, 1 cross 1 cross 1, followed by 3 cross, those parallel connections. So those are the fundamental blocks. So you decide what type of fundamental blocks required and then how much of them you put. So that kind of defines your architecture. Choose a basic block. Like if you're designing from scratch, you can pick the basic block and scale it based on the compute available. You could use those efficient net rules to scale them, right? So yeah, fine, I have picked my model. What? Did someone say something? Okay, so yeah, I think we pretty much have what we need, right? So how would you train a model? Like a rough pseudocode shall we write here? Training is CNN. So we have defined different things, right? Datasets, hyperparameters, models. So in what order do I do what? First thing is we should prepare data, right? Like I prepare data using some create a data loader of the bird species data. So what all parameters would I have to set when I'm passing through data loader? usually? Batch size. Batch
Transforms.
batch size and transforms, which are the pre-processing steps, no? So these things I would give to get my data loader. Then you get the train data. Well, test all of them from our data, or like create them separately also, whatever. One. Then what else do we define before I start my training loop?
We send this data to the device like GPU, CPU.
Yeah, fine. Put it to device, to GPU. Usually it's not done here, it is done in the loop once I load it, right? So this is when I am creating the data loader, I am not actually loading the data into the model. So I'm just defining where what is there, so that in the training loop it can fetch it. So I'll the training loop will give its indices, so it will fetch that batch of data, and then we put it to the device. So when data loader is created, it's just creating a pipeline from where to get data from, okay? So what else do we need? What else do I define here before my training loop?
And loss function.
Loss function, yeah. So define your loss criterion. Like C loss I'll call. So this is usually also a class, right, which will have its function which gets called, or you can actually implement the loss in your loop also, but fine, I'll just call it. C loss and all standard losses have classes to them. Then what optimizer I'll have to define, like say Adam. What will I give? Learning rate usually. And then these things have like momentum parameter usually, and yeah, depending on the parameter you can define what these things are. Optimizer. What else?
We load the model.
We load the model. Then we load the model. So our model, which model shall we pick? The gold standard ResNet, say ResNet 50. So ResNet 50 a load. So yeah, usually even this parameter initialization, when you load, like call the definition in the init function, it would be usually defined, so that it will initialize the weights also. It's not done specifically outside in general. But suppose you want to load a trained model, like imagine a trained model, then you will have to load the weights also. If you want to do transfer learning or fine tuning, load weights. If fine tuning, so fine, now we have model, optimizer, loss, data, training data, everything. Now I will go in loops, right? We have defined the number of epochs, no? So my outer loop will usually be the number of epochs. Define this, it would be this. Say I have some 10 epochs of data, 10 epochs over data. Now my inner loop will be in so I iterate over the training data. So I get one batch at a time. Then what do? I get the batch. First thing is what?
Send the data to the device.
Send the data to the device. Sure. Two kuda I've done, suppose. Fine. Oh yeah, here model also we'll have to put it to the device. Model can be done once. It's one time thing. So data is yeah. This is my data. Then I pass it through the model, right? And I get my features. Features or the final layers only, logits sometimes. Logits. Oh yeah, here usually you'll have to define the number of classes to define the last layer. No, if I have say 100 classes, based on what the number of classes is, it will put the last layer. For ImageNet it was 1000, but otherwise we'll have to specify that. So logits will be what I pass through the model. I pass the data through the model and I get my logits. Then I get compute the loss, right? So I'll compute the loss on by passing it through the loss criterion. Loss criterion, what all should I give when I pass it to the, what are the inputs to this loss criterion?
Logits and labels.
Logits and labels. Oh yeah, so this batch data will usually have both, no, like x and y will be which I can get from the data. Logits and the x can be the images and then its corresponding labels. So I pass this. Then what do?
Backpropagate.
Loss dot backward to backpropagate. So when I do loss dot backward, what would happen? The gradients would get computed. But I also want to update the gradients. So how do I update the gradients? I do the optimizer thing, no? Optimizer dot step. Oh yeah, Adam learning rate and I have to define the model parameters here actually. First define the model, then the optimizer. So here I should pass the model parameters. What are the parameters I'm updating, right? That I should have passed to the optimizer. So I do optimizer dot step. When I do this, all the parameters which I would have passed here, no, it need not always be all the parameters. Sometimes I might do some specific parameters, whatever, but whatever gets passed is defined in the optimizer, those get updated. Once I do optimizer dot step, I also do another step called optimizer dot zero grad. So this is a very important step actually. So when I do this loss dot backward, all these gradients would have gotten computed, right? And those gradients would be used in the optimizer to do this step. So by doing this zero grad, it gets rid of these gradients, because the next time I want to use the new gradients that are computed, not and get rid of the old ones. So you should always do this optimizer dot zero grad. So that's it, right? Pretty much the training loop. Then once in a while I can do the validation and testing once I come out of it. Oh yeah, this usually what we do is put this model in the train mode. So by putting in train mode, yeah, so there are some layers that work differently in training and test mode. Can you name a layer which works differently in train and test? For that sake, you
Dropout,
need to, yeah, which one?
dropout layers.
Dropout, yeah. Dropout works differently. Anything else? Even batch normalization works differently. Because while training, it will use the batch mean and variance. While testing, it will use the stored mean and variance. So, and then while you're testing, you put the model to evaluate mode, and then this iteration would look the same way, just that I would have this part. I use the logics and then I get the prediction. I'll not have this loss computation, backward and optimizer step, these parts, right? Okay, now let me go over the notebook. It'd be easier to. Okay, here they have defined this class unnormalize. Where will I use this unnormalize? It is undoing the normalization, no? If my data loader has already done the transforms, and suppose I want to visualize my image, then I can call this unnormalized function, no? If I have to check which data point what is happening, visualize and see from the data loader itself, can use this thing. So here we are defining these data loaders for MNIST. What all I have specified: batch size, number of workers, validation fraction, train transforms, test transforms, all this. So train transforms, so here they're not doing anything, they're just converting it to a tensor, right? Like the model, the data would be as like some numpy arrays, right? Which I want to convert to CUDA tensors, so I put this to tensor. Test form transform, so this is the bare minimum required transform, so this has to be always done. Plus over this I could do other things, right? Like mean variance normalization and so on. So here I'm using that torch vision. This is all there in torch vision datasets, no? Yeah, from the torch vision datasets, the standard datasets are available. So I can load the SEMNETS data just by specifying whether it's train or test and so on. So here this will load the train dataset, validation dataset, test dataset. Yeah, so once I have this, I first get the datasets, then pass it to the data loader where I give the dataset, specify the batch size. So these two things are drop last and shuffle. So shuffle is to shuffle the dataset, right? So drop last is usually, so that's what, right? Now I have 1,000 images and I set uh, batch size of 32. So 1,000 is not a multiple of 32, right? So in my last batch, I would have images that are lesser than 32. In such cases, usually they just skip that one. But because I have shuffle equal to true, I'll still be seeing the images somewhere in the later epoch or something. So they just drop the last batch. While testing, do I need to shuffle? No, right? So I just set it to false. So similarly, this is data loader for CIFAR 10 dataset. And this one, yeah. for evaluation. Okay, some functions for evaluation. So set all seats. So yeah, these are all the things which can be inducing some randomness in your code, right? The torch, the random library, NumPy has all of this. So if you set a seat, then your experiment would be reproducible. The way in which, so even if it is shuffled, the order in which the data would be arriving would be same if I set all the seats. And so these are also some some functions can be non-deterministic. So to make that deterministic, and you can set these things as true. So this one computes the accuracy. So I get what all do I need? Model, the data loader, and the device is where to load the device. I mean load the data to it. So I iterate over the data loader. So we get features and its labels. Features, I mean images only in this case. They've just named it features. So I put them to device, the CUDA device or CPU or GPU, whatever is there. And then I pass the model and the data to the model, get logits. Then on axis, so why am I doing this max over 1? Hmm? So suppose the batch size is 32. What would the and 32 and I am doing over MNIST dataset, that is 32. Number of classes are 10. Then what would my logits dimension be? What would the logits dimension be in this case? It doesn't matter what the model is. My final classification layer output, I've specified the number of classes, so I should know what my output size will be. So what would this dimension be?
10 cross 10.
Not 10, 32 cross 10. So usually in all your computation, the first dimension will always be your batch size. Everything else comes in the later dimensions. So it will be 32 cross 10. And even these, no, this will be like 32, the batch dimension, cross the image dimensions. In MNIST, it is 28 cross 28. It will be like this. This will be, labels will be 32 cross 1. So the first dimension will always be the batch size. I have 32 labels, right? 32 images, each of size 28 cross 28. Because MNIST is an RGB image. Is a grayscale image. If it is RGB, you'll get this, either this or sometimes channel dimension can be here. So this logits, this is over 1 because the classes dimension is the first dimension, as in, so this 32 is the 0th dimension, right, in the in Python. So 1 is my second dimension, which is the rows. So along the rows, that is among the 10 classes, I am picking the maximum score. So that is why I have torch.max of logits along axis 1. And I would get, so max actually returns what the maximum value is, and this is the value label. This is the index, and this one would be the value max. This will be the max logit, which I don't really need. I only care about which label it is, right? So number of examples seen until I'm computing accuracy, right? So the number of examples seen until time until that step, I keep accumulating. Targets dot size of 0, that is in the 0th dimension, what is the size? So 32, no? So this will be 32 actually, return 32. Correct predictions in that batch, that is how many times the predicted labels is equal to my targets. So this will be a boolean array and I sum over it. So it would give the number of times of 32 images, how many of them are correct. So I keep storing them, iterating and updating these two values. So once I have gone over the whole data loader, my total final accuracy is the total number of predictions which were correctly classified, which images which were correctly classified, divided by the total number of examples into 100, right? Similarly, they have this function to compute confusion matrix. Uh, do you guys know what confusion matrix is? So have you heard of what confusion matrix is? Means?
Yes, a matrix of true positive and false positive and all.
Yeah. So I have 10 classes here, right? But my image if can get classified into any of them. So it calculates. So if I have a cat image, if at all it calculates, if it puts into the clash dog, and so I increase the entry in that space, like the wrong entry. It is a yeah, so I compute this whole matrix where one axis is for the ground truth, other axis is for predicted labels, and how many of ground truth images of cats get is distributed over all the 10 classes as predictions. So by computing that, seeing confusion matrix, we can know which classes are getting confused into which other classes, and so on. So yeah, this is the loop for training. So what all are passed? Model, the number of epochs, train loader, validation loader, test loader, optimizer, device, scheduler. So scheduler is also for optimizer. No? Yeah. So this one is they accumulate what the loss is and the accuracy at different time steps of what on training and validation data. So it's just empty list. So I'm defining the number of epochs, right? So outer loop is the number of epochs, the inner loop is on the data set. I get the features, the labels, pass the data to the model, get my logits, then pass it, compute cross entropy loss, for which I give the logits and my targets vector. So optimizer dot zero. Yeah, this zero grad can be either done here or after optimizer dot step. It's the same. Basically, it should come in loop. That's all. So optimizer dot zero grad would clear any previous gradients. I do loss dot backward to compute the current gradients for this loss. Then I update the model parameters. Then this part I'm just logging this data, like what at which epoch for this batch what was the loss. So that is logged. Yeah, after I do this. Okay, after every epoch I put the, so this is one iteration, right? I mean one epoch. This whole thing is. So after every epoch I put the model to the evaluation mode, and then I compute the training accuracy and validation accuracy. So these also I keep logging them, printing them, and if I have a scheduler defined, then I apply this step. Yeah, and once you finish this whole training and validation step, you come out. Then here we are printing the total training time, and this is the test accuracy. For test accuracy, we pass the model, the test loader, and the device. Get the test accuracy. So yeah, here we have got all these logs, right? From the yeah, the mini batch loss with time. How did the loss change? How did the training accuracy change? How did the validation accuracy change? So all of that. So yeah, these helper functions are there for plotting those training loss accuracy. Visualize some examples. So plotting the confusion matrix. So So all we had defined all the functions. Now we'll actually run them by setting the seed. Batch size 250 is set as 256 here for 5 epochs. We set all the seeds. Load the training CFAR 10 data set. Now this is the this is the model definition. So here I think they have defined ResNet block. So this is the ResNet block. So ResNet has one. So this is the basic block of ResNet. Where this is the basic block of ResNet, which has convolution layers followed by batch norm and ReLU. Again convolution, batch norm, ReLU. So this is like one ResNet block. So and they have these bottleneck layers. So here anyway this is the whole network definition. So here we are defining the model, optimizer, scheduler, then we are calling the training function, then we are visualizing the training loss, see how the accuracy changes with time. So CFAR has, this is CFAR dataset which has these 10 classes here. So and the dimension here is also 32 cross 32. And all the images in the dataset are already mean variance normalized with like 0.5, 0.5, 0.5 mean and the standard deviation. So they have this unnormalizer defined here, and here they visualize some examples. So these are really small images actually which have very bad resolution. This is what the model. Okay, let it run here, but this was the previous iteration when it had run. So it's originally a cat. P is the prediction, T is the target. So which are the misclassifications here? Cat. It has predicted cat for frog, but it is really hard even for us to classify some of these here, right? So in such cases, like if you use some augmentations and so on and train the model, it will be more robust. Okay, this is going to take time, but anyway, you guys have access to these notebooks, right? You can try it out. just run it for one epoch and show it to you. Oh yeah, after one epoch it would have collected only one element for accuracy plot and all.
Excuse me, can we get the code? Where is this code available?
It is there in this GitHub site.
I'm not into GitHub then.
Okay,
Can
I'll
you
post
put
the
the
link here.
link?
Yeah, this is from an earlier. So yeah, the numbers, lecture numbers might not match exactly, but all the notebooks are there.
Okay, fine.
You can go over the weeks, and this is in week 5's content. You
All
can,
are there in the
yeah,
that
all
GitHub,
weeks
right?
content is there. You can check out the notebooks from there and play around with it. Yeah, so yeah, this shows this is the loss plot, right? And I ran only for one epoch, right? So yeah, so accuracy plot didn't show up because there was only one item. But anyway, you can try it out on your own. Okay then. See you next week.
Thank you.
Thank you all for attending.
Thank you, ma'am.
Thank you.